In this presentation, I'm going to talk about using Aspen to select vapor-liquid equilibrium properties. So the idea in Aspen is that, of course, if you've used it before, and I think you all have, you need to specify your components and properties in the first place before you can begin doing any kinds of calculations. So what we're going to learn in this presentation is how to specify your components, how to indicate the property method you're using, how to specify interaction parameters which go into the property method, how to access the NIST database, how to compare models to data, and how to perform regression to get new parameters or improved parameters. So first of all, now this is for a specific version of Aspen. It's Aspen Plus version 8.8. All of the components should still be there even if there are changes in future versions. So keep that in mind. The things I'm describing you can find based on either searching online or through the documentation with your current version. Now, as far as specifying components, you need to find the component menu on the left-hand side, which is here, and you need to specify what components you actually have. The easiest way to search is by the component name. You can give component IDs, but the name usually you want to actually search in order to be able to find the right components. So for example, you could add ethanol and you could add benzene and whatever your mixture actually contains. So hopefully this is familiar. Also remember that as you're going along, Aspen gives you hints about what it wants next. So when you see blue checks like you have here, because this actually isn't a relevant property, that means that Aspen is happy and ready to continue. Now once you have your components, you have to choose what vapor-liquid equilibrium calculation method you want to use. And so that you do that by what we call method selection. So first of all, we need to go to our specifications in our methods, which appears here, and you choose your vapor-liquid equilibrium model. Now obviously there's a huge number to choose from, so you may need some help deciding what you're going to use. And there's this methods assistant, and in this version it's over on the right hand side, and it will take you through basically a wizard and ask you a few questions to decide what's a reasonable guess for our property method. And by property method, what we mean is what activity coefficient model are we using? So one property method is ideal mixing, which means that you use Raoult's law, but that's rarely what we can actually use for real mixtures. So you might find the Wilson equation. There are some models that have to do with the non-ideal behavior in the gas phase. So this property methods assistant is going to help you to decide what to do. So if you select that, we're going to take a specific example in order to go through that. So let's say we have an ethanol benzene mixture. It's non-ideal and it exhibits an azeotrope. So any mixture that has an azeotrope cannot be modeled with ideal vapor-liquid equilibrium behavior. So we want to compute VLE for this mixture using different thermodynamic models, compare the results with experimental data available from the NIST Thermo data engine, and we're going to perform data regression to get new parameters for a different model. So first of all, the NIST Thermo data engine. You can find it on the home ribbon. Again, this is for this version of Aspen, but it's right here. It says NIST, TDE, that's the Thermo data engine. And the idea is that NIST has basically, that's the National Institute of Standards and Technology. They have gathered together reliable sources of data. Now, they're not all equally identical. We're going to see that there's actually a lot of information available, but these are from journals and from handbooks and reliable sources of information. So if we have a binary mixture that we're interested in this case ethanol and benzene, we select binary mixture. We also have pure component properties that we could use. Sorry, I don't know how to go back. But once we have our components that we're looking for, when we search, we're going to get a list of all of the possible data sources that are available. And what you find, they have arbitrary numbers. So there's binary VLE 004, binary VLE 007. They all correspond to specific sources of data. And what you see is a year that it was published or printed, a temperature range over which the data is available, and then the pressure range. So you want data that are consistent with the pressure and temperature range that you want to use for your actual problem. So that will help you to narrow down which ones you want to use. Also, it tells you how many data points were used or how many are available in that source. So you'll notice that in this example, we're going to choose binary VLA 017 for the benzene ethanol mixture because there are 39 data points. It was published in 1952. Don't let that bother you. Measuring vapor-liquid equilibrium data is not that hard if you do it appropriately, if you're careful. Now the pressure is, let's see, this is in pascals, so about 101 kilopascals, which is atmospheric pressure, and the pressure range, or sorry, the temperature range is 341 to 351 Kelvin. Usually that's going to be the range that you need to cover all of the vapor-liquid equilibrium, so that's fine. So we're going to choose these isobaric data at approximately atmospheric pressure and see what we have. So when we do that, what we actually get in our retrieved data is a table. And so we have a liquid mole fraction of ethanol, temperature, vapor mole fraction of ethanol, and the total pressure. Notice the total pressures aren't changing because these are isobaric data, but that is always there. Also notice that at the bottom, the entire reference is provided. And this is a journal article. So you could go look it up and verify that these are the same data. So the nice thing about Aspen is that it's already done that. It's already gathered all of this together for all of these common components in mixtures. You need to save the data to make it available, but once you've done that, you'll be able to work with it. So now if you go to the data heading over here on the left-hand side, you can see BVLE 017 is there. And we can look at the data in this data tab that appears here. But what we can also do is to generate thermodynamic diagrams. And what's usually the most useful thing for us is a TXY diagram or an XY diagram. And so you can directly plot the data right away. We can use it other ways. And so if we generate a TXY diagram and have Aspen plot it for us, this is what we get. And this is showing all of the data. And these individual data points are what were reported in that reference. So, at this particular temperature at 343.1 Kelvin, or whatever the temperature is, the liquid phase mole fractions, and I don't know if these are repeated measurements, probably that's what that represents. This is the liquid mole fraction, and this is the vapor mole fraction. And then at a temperature of 345.1 Kelvin, this is the liquid mole fraction, and this is the vapor mole fraction. So all of that is gathered together, and you can see the data. So that's a really handy resource. Now what we want for our actual calculations is not individual experimental data points, but we want to have a choice of a method and a set of parameters that will match these experimental data. So in order to do that, we need to choose a property method. So one way to do that is, and I've got the reference for this down below, William Wilcox published this. It's basically a wizard or a flow sheet that asks a few questions about your mixture. And so the first question that it asks is your mixture polar or nonpolar? In our case, because we have ethanol, that's a polar component. It's got, it's sort of the nonpolar end, which is the ethyl group, and the polar hydroxyl group, so overall the molecule is polar. And if at least one of your components is a polar molecule, you should go with that. So we make that decision. The next question, does it contain an electrolyte? An electrolyte is a salt. And basically, it's only two solvents, ethanol and benzene, so there's no electrolyte, so it's a non-electrolyte mixture. And we've gone through this part of the flow sheet. There's more to it. There's a star. We're going to follow that star on the next slide. And we keep going. The next question is, what pressure range are we interested in? We are less than 10 bar, so that's the upper part of this flow sheet. Next, what's this question? Do we have liquid-liquid equilibrium or not? Or sorry, IJ, what's IJ? Now I forget. Interaction parameters are available. Do we have interaction parameters? If the answer is yes, so we're either going to find them experimentally or find them in a database, which means, so I guess I should back up. Sorry, I forgot about this part of the flow sheet. So what the question is here is, do we have parameters that could go into a thermodynamic model? such as the Wilson equation, the NRTL model, or a thermodynamic model for activity coefficients that depends on experimental parameters? If the answer is yes, then we can use this part of the flow sheet. And then we decide whether or not we have liquid-liquid equilibrium. And that's something we may have to iterate to figure out whether or not we have for our system. But for ethanol and benzene, they don't form two liquid phases. So the answer is no. And our choices, notice this doesn't give us just one answer, but our choices for possible vapor-liquid equilibrium models are the Wilson equation, NRTL, and UNIQUAC. And there are other variations, but those would be good places to start. If we didn't have the interaction parameters, the UNIFAC model is actually a way to basically predict thermodynamic information without needing those. So we want one of those models. And so what we're going to do is we go into our methods and specifications, and we choose our base method. So that's the method that we're using for our vapor-liquid equilibrium calculations. And you can see that we're going to use the NRTL method. That's one of the two things that came out of that flow sheet. Set that as the base method. And in Aspen, if you have common components such as benzene and ethanol, if you just go into the binary interaction parameters and look, and we look for the NRTL model, which was our method that we chose, we already have parameters there. So for example, the Aij value is specified, and it's blocked by the text that was there, but there's a Bji parameter, for example, and there's an Aij and a Bij. All of those parameters are already automatically loaded once we chose the method, if those are available for our mixture. So we already have parameters. The question is, how well do those match the experimental data that we chose? So we have experimental data, and we have database parameters. They don't necessarily match. And so it's always good if you have experimental data. The best proof that you've chosen a good model and good parameters is to show that the TXY diagram you calculate using those parameters matches the experimental data. So what we can do next, is we can take, so basically we've chosen a property method already, and when we go into our binary analysis, and up here, this is the binary analysis menu. When we choose that, we can choose our components, ethanol and benzene. Here, we want a TXY diagram as for the type of analysis. And we choose the number of points, although the default is fine. We choose our pressure. We want that to match, because if we don't choose the right pressure that matches our data, we wouldn't expect it to match. And we choose our property method, just confirm that it's consistent with what we want. Just make sure nothing went wrong. And then we run the analysis, and we will get calculated TXY values. And by default, you see the TXY diagram, and these are all the calculated points and the XY values that go along with it. So it looks pretty good, qualitatively speaking. There's an azeotrope. It kind of looks generally like the experimental data, but we actually want to compare to the experimental data. Notice that the default axes for this plot are different than our experimental data. So for example, the temperature is in degrees Celsius. So in order to be able to compare, we need to make sure that we have the same axes on the two graphs, and we're going to need to combine them and make it a common axis. So notice what's going on here. So this is a plot that contains both the experimental data, that's the points, and the predicted NRTL curves. We have the mole fraction of ethanol on this axis, so that's consistent, but we have two axes on this side, and one corresponds to the experimental data, and the other corresponds to our calculations with the NRTL model. We want those to be the same, but they're not. So for example, the lower bound is 340 and 341 for the two plots, and it's 351.5 and 354. So if our axes don't match, our curves are not going to match. So we need to correct that. In order to get a single axis, what we need to do is to right-click on the plot and then go to the y-axis map. And that's going to allow us to produce a single axis. We also want to, for the model prediction, right now it has points like here, here, and here. It's usually clearer if we get rid of those points for theoretical predictions. So we want to use line only, or eliminate the markers or the dots that appear on that prediction. And that's on the Format tab, which you can find when you hunt around, and you can use the Aspen documentation to help you. So once you've done all of that and reformatted your graph so that you have the same axes, so you only have one axis vertically, and you have mole fraction of ethanol on this axis. Now the curves are the NRTL calculation with the default parameters, and the points are the experimental data from the reference that we saw earlier. And what you can see is that this looks like a good model. Qualitatively speaking, it matches the experimental data really well. And it could even be that those experimental data were used in order to get the parameters that appear in the Aspen database. So this is our comparison. In your design project, if you want to show to me or to the reader that you've chosen a thermodynamic model that matches a set of experimental data that you pull out of the NIST database, this is the way to show it. You want to make a plot where you calculate using your thermodynamic method what the curve looks like, and that's, this purplish blue line and this reddish line. That's the theoretical prediction for, this is the bubble point curve on the bottom and the vapor point curve on top. This is bubble point and dew point curve. Show me on a single plot that those match. And that would be the best way to show. That's the best evidence that you have a good choice of a thermodynamic model. Now, from our initial selection process, we actually had more than one possibility for what thermodynamic model to use. Is it possible that others might work? In brief, the answer is yes. I mean, the Wilson model might match the data equally well or approximately equally well. So how do we decide which model to use? The best answer is not the model that makes the separation easiest. And I've seen that on past design projects. Sometimes the argument is, well, if I choose this particular thermodynamic model, I need fewer stages. Therefore, I'm going to use the Wilson equation instead of using Uniquac. That's not really the best answer. The best answer should be what agrees with experimental data for vapor-liquid equilibrium, because that's what you want to be your basis for your design, not what gives you an answer that you like. So we can compare to an ideal model, for example, but we're probably going to find something bad. And then the other thing that we want to look at is, what if there are no parameters for the model that we chose in our database? If that's true, then the Unifact group contribution model can be used. It's a little bit more complicated, and you'll have to get familiar with the documentation, but you can do it. Now, if we want to actually pick a model and parameterize the data, meaning we choose the parameters that go along with the model, we can do that. And here's an example, just again for the ethanol benzene mixture. If I've already selected those as my components, but if I look at the Peng-Robinson equation of state as another way of doing the vapor-liquid equilibrium, if I choose that as my property method, and I look at my binary interaction parameters, what I find for PRKBV1, I don't have any parameters there. So if I were to try to look at the predictions, I think what it's going to do is to assume that it's an ideal mixture, but it's not going to work very well. It's certainly not going to match the experimental data. If I want to find parameters that match the experimental data, I can do regression. So this menu over here on the run mode, if I choose regression, what that means is that I want to find parameters so that my vapor-liquid equilibrium data are going to be matched by the model that I choose. So in the setup, I need to choose the data set that I'm using. And I think that's self-explanatory, so I didn't show it here, but you choose the data set BLE017, the one that we selected for our system. And I guess before we start, we need to make a new regression. And it gets called DR1. That's just by default. So they'll get numbered sequentially if we do more than one. And we need to select the parameters as they're set up here. So if we have a binary mixture, we have to set up the parameters this way. And just do it that way. You can look into the documentation if you have a more complicated mixture. But for anything you do for me, you'll definitely not have anything more complicated. This will probably get you pretty far in design too. So this should be enough. And then you say run. So this run over here, just like doing any calculation in Aspen, if you choose run, so there, I figured it out. Okay, so we can go backwards. So basically it's a bad match between the experimental data and the model. So if you had to choose, what we started with, the NRTL model was a better choice. Now Now, if you had nothing else, maybe you would go with a less than ideal model, but if you can find a model that fits better, that's what you should go with. So, I hope what you learned from this, obviously property selection is crucial. You want experimental data, and you want to choose a thermodynamic method, meaning the activity coefficient model and possibly a non-ideal vapor model that's going to match your experimental data. So the things that we learned in this video are, first of all, that Aspen provides experimental data through the NIST database. So you should be able to search that and find vapor-liquid equilibrium data for the mixture that you choose. If it's not there, that probably means you have a relatively exotic mixture, and you may have to choose a different property model in order to be able to use it. There are a lot of options available for a given mixture, so no one's going to judge you as long as you are clear about what you're assuming. So if you choose a particular reference, cite that reference. You hopefully should be able to justify why you chose it, but nobody can say choosing one reference over another is better unless there's an obvious reason. If necessary, you can use regression to find model parameters, but for a lot of common mixtures, like THF and water, you're just going to find parameters built into Aspen. So all you really need to do is to verify that the property model that you choose is a good choice, and that should be enough. With that will conclude this presentation.